Hello everyone, I'm Bruno Picard from Fluctus, emitted from a small town called Rabastens in France, and I represent today the results of a study dedicated to determine how water vapor climate data records can help to estimate a long-term stable Earth energy imbalance record. This study is funded by CNES and led by Benoit Meyssignac from CNES. The team also gathered Barnoud, Florence, Marti, and Michaël Ablain from Magellium, Toulouse in France. So first, I will guide you to a small trip to better understand how energy imbalance on one side and water vapor on the other side are related to each other. The EEI, as you well know, is defined by the difference between of about 1 watt per meter square between incoming and emitted radiation. Since the ocean concentrates the vast majority of the energy uptake, the variations, the trend of the ocean heat content, called GOHC, places a strong constraint on the absolute magnitude and the uncertainty of EEI. Benoit Meyssignac and his co-authors demonstrate in a dedicated paper in 2019 how the GOHC can be estimated from special missions through the measurements provided by gravimetry, as the GRACE mission, and altimetry, as Jason's series or Copernicus Sentinel-3 missions. Compared to other techniques relying, for instance, on in situ measurements, the spatial approach benefits from better spatial and temporal sampling, but with the drawback of larger uncertainties on the estimation of the GOHC trend. Now, the major source of uncertainty on the global mean sea level, as provided from space altimetry missions, is the wet tropospheric correction, WTC, that estimates the delay on the radar altimeter range due to the atmosphere refractivity. On altimetry mission, a microwave radiometer is dedicated to the measurement of the WTC, but potential instrumental drifts may have an impact on the WTC long-term stability that directly impacts the WTC. Plus, the associated uncertainties on the WTC stability are large. By its definition from the atmospheric refractivity, the WTC is strongly related to the water vapor and can be estimated from the total column integrated water vapor, TCWV, using a polynomial fit as demonstrated by Kem et al. In 2000. Now coming back to the core of our study, climate-oriented water vapor are available with a large and specific effort put on their stability. We will study here two datasets, one provided by Eumetsat CMSAF called OPS and based on SSMI radiometer series. The other one provided by REMSS company and based on a mix of SSMI, SSMIS, Eumetsat, and Eumetsat radiometers. Both datasets are assessed in a paper by Mark Schroeder in 2016, leading to the characterization of the trend of about 0.03 kilogram per meter square per year. But we especially interesting here in the estimation of the uncertainty of 0.007 kilogram per meter square per year. Roughly translated to WTC, the uncertainty is 4 to 5 times better than the current assumptions of 0.2 mm per year made by Michaël Ablain et al. In 2019 in a paper dedicated to uncertainty on GMSL trend. Now that the relation between EEI and WTC is more clear, or I hope so, here is the objective of this current study. The question is, could those datasets be used to compute WTC, to reduce the uncertainty on GMSL, reducing the uncertainty on the GOHC trend, and eventually on the EEI? So to be even more clear, this study is the first attempt to better constrain the EEI and is focusing on the uncertainty of EHC trend or GMSL and WTC. So this study is not a proposal for a better WTC correction, with respect to altimetry mesoscales. Some datasets exist that aim at providing a better long-term WTC for climate study purpose. I can cite, for instance, the important work made by Joana Fernandes from the University of Porto on this topic, and I invite you to see the presentation given by his collaborator Telmo Vieira in this very same session. But given the objective of this study, we needed a more direct approach to better handle the uncertainty propagation through the system. So the next step would definitely be to include a comparison to existing dataset. As previously said, a polynomial fit can be used to find a relation between wet tropospheric correction on one hand and water vapor on the other hand. For this first approach, we needed a single correction that would be applied to the whole area. So using ECMWF era 5 dataset, we propose to compute the polynomial fit for every month between 2010 and 2020, and to use the average value of the polynomial coefficient. This approach comes obviously with strong assumptions on the stability of the relation between wet tropospheric correction and water vapor through time and the role of the temperature, and we will come back to that later on. Estimating the uncertainties from the proposed approach is a work performed by Barnoud, Florence, Marti, and Michaël Ablain from Magellium. Given the complexity of a formal mathematical approach, an empirical approach has been preferred to propagate the uncertainty on water vapor onto the wet tropospheric correction. In order to assess the impact of uncertainty on water vapor trend, we defined n solutions of water vapor trend using Water Vapour CDR and the following model. A full domain of different trends is explored through a Gaussian distribution on the slope A, the standard deviation being defined by the uncertainty provided by Schroeder et al. Then, n solutions of WTC are computed using the previously defined polynomial relation, and temporal fit are then estimated, and the uncertainty on WTC trend is eventually defined by the standard deviation of the slopes A. The same approach for the impact of the uncertainty on the bias B for water vapor and the uncertainty of the polynomial coefficient is used. And here are the results of the different uncertainties found using the empirical approach. Given the known limitation, FCDR-derived wet tropospheric correction trend uncertainty is an uncorrelated drift type uncertainty of about 0.05 mm per year, whatever the CDR, whatever the period. This is to be compared to this historical uncertainty of 0.2 mm per year, and the uncertainty variance is then reduced by 94% for periods shorter than 5 years. The huge work of the introduction of the new wet tropospheric correction computed from the CDR water vapor on the EEI computation system has also been performed by Magellium. This work is also focusing on the definition of the uncertainty, its propagation in the system, and the characterization of its impact on the uncertainty of EEI. I invite you to see the presentation given by Florence in the very same session for more details. I will now present the main results covering the GMSL period from 1993 to 2013 and the GOHC EEI period from 2002 to 2014. Those results consist on a proof of concept and still some additional investigation before a robust operational product are needed. On this figure, you can see the difference between the wet tropospheric correction CDR time series, the new one, and the historical radiometer WTC from 1993 to 2015 using our EMSS in green and OPS in yellow. The impact is quite consistent over the era, when larger differences are observed with JSON3. This may be due to the fact that JSON3 WTC is not yet reprocessed and everything has to be confirmed. This table sums up the results for the main climate indicators. Using the current approach, the GOHC trend and the mean EEI are increased by 10 to 20%, and the variance is reduced by about 20% with respect to the previous assumptions made by Ablain et al. In 2019. In conclusion, using FCDR total column water vapor data and a polynomial model with robust coefficient estimates, a new wet tropospheric correction is computed and applied to altimetric sea level data. This study assesses the impact of the FCDR-derived WTC on the GMSL trend, the GOHC trend, and the EEI mean estimates and their associated uncertainties. Given the lack of information on the uncertainty of the water vapor dataset, an empirical approach is used to propagate the water vapor trend and bias uncertainties to the derived global mean wet tropospheric corrections uncertainties. Over the period covering 2002 to 2017, the GOHC trend, previously estimated at 0.8 plus minus 0.11 watt per meter square with the usual radiometer-based wet tropospheric correction, is now estimating to 0.9 plus minus 0.10 watt per meter square using our EMSS FCDR data. This corresponds to a trend increase of 10% and an uncertainty variance reductions of 18%. Now some limitation and possible improvements. The uncertainty information on the FCDR water vapor is limited to the global mean trend uncertainty based on Schroeder et al. In 2016. Our computation model leads to a water vapor trend of about 0.06 kg per meter square per year, which is quite different than the trend of 0.03 kg per meter square per year estimated by Schroeder. Our uncertainty analysis does not take into account some of the sources of uncertainties, especially neglecting the effect of the temperature dependency between wet tropospheric correction and water vapor. And finally, some recommendations. So users of CDR water vapor would greatly benefit from a better description of the uncertainties on those datasets, including a covariance matrix of the errors, and this is a question for the globe vapor group inside GOHC. On the other hand, the altimetry system could also benefit from a new combined product, combining high-frequency wet tropospheric correction as estimated from the radiometer and low-frequency CDR wet tropospheric correction as we propose today. We would use our EMSS dataset with a better operational availability. So this raises the questions of the future plans for HOPES, and this is the questions to Eumetsat. Also, the current CDR WTC product is to be assessed against existing products, including CCI GPD Plus solution proposed by Joanna Fernandez and her team. Okay, thank you for your attentions, and don't hesitate to send me any question you would have.